This is Planet X, and Blorg is its emperor. Unfortunately, the neighboring Planet Z has indicated that they plan to invade Planet X. Blorg therefore wants to evaluate his defensive capabilities. In particular, he'd like to know the fighting prowess of his people. He decides to use a combat simulation program to score individuals on their combat ability. Ideally, Blorg would administer the simulation program to every single adult inhabitant of Planet X. Here's the score for Zoran, here's the score for Lendig, and so on. Here are all the scores that Blorg would end up collecting, millions of them. If Blorg had the time and resources to score every single adult Planet X resident, he'd end up with a picture of the population distribution. And then he'd know everything there is to know about his fighting force. The population mean combat score, for example, is 40.8. The median is 37.8. The SD is 18.1. And the IQR is 23.5. Unfortunately, Blorg can't afford to give every resident the combat test, so he doesn't get to know the population parameter values. Instead, he decides to collect scores on a simple random sample of size n equal 1,000 adult Planet X residents. Administering the combat simulation to this sample, we obtain 1,000 scores. In the sample, the mean is 40.9, the median is 38.4, the SD is 18.3, and the IQR is 22.8. So, for example, Blorg can estimate the population mean to be 40.9. And that's encouraging because his simulations indicate that a fighting force with an average combat score greater than 35 will be able to repel an invasion from Planet Z. Technically, this would be expected to hold as long as the SD is less than 30, which appears to be a reasonable assumption based on the sample data. But Blorg, having taken statistics as a young alien, knows that the results he sees based on a sample, the sample statistics, are not exactly the same as the corresponding results for the population parameters. In particular, if he were to collect a different sample of n equal 1,000 adult aliens, he'd expect to see different sample statistics. Had he collected this sample, for example, he'd have seen these sample statistics instead. So how can Blorg be confident in anything he sees with any one sample? Well, let's imagine the collection of lots of samples, and let's keep track of all the different sample statistic values that we observe. Here we go. With each sample of n equal 1,000 individuals, we see a different set of sample statistic values. Different means, different medians, SDs, and IQRs. So we just collected 5,000 samples of size 1,000, and now we have these distributions of our sample statistics. What we've learned then is that because our samples are random, our sample statistics are themselves random. They therefore have their own distributions, and to make it clear that these are distributions of sample statistics, these distributions are given a special name: sampling distributions. What does this mean for Blorg? Well, these are the sample statistics he observed for his original sample, and what we now know is that these numbers are realizations from their respective sampling distributions. For example, the sample mean of 40.9 can be viewed as a random draw from the sampling distribution of the sample mean. How can Blorg use one realization, the 40.9, to say something confident about the population mean? Let's look more closely at the sampling distribution of the sample mean that we just simulated. It turns out that with a large sample size, and a rule of thumb is that a sample size of at least 30 is large, with a large sample size, the sampling distribution of the sample mean is approximately normal. We also know that the mean of this sampling distribution is equal to the population mean, and the standard deviation of this sampling distribution is equal to the population standard deviation divided by the square root of the sample size. In other words, this is the theoretical sampling distribution of the sample mean. So our observed sample statistic, the sample mean of 40.9, is a random draw from this normal distribution. If we knew the value of the population mean and the population standard deviation, we would know this sampling distribution exactly. We also wouldn't need statistics, as we could just check whether the population mean is greater than Blorg's target combat score of 35, and we'd be done. But here's the magic part. Let's assume that the population mean combat score is equal to the threshold value of 35. Then our sampling distribution would be centered over here. Then sample means to the left of 35 would be indicative of a fighting force that's too weak for Blorg's needs. And sample means to the right of 35 would be indicative of a strong enough fighting force. In statistical inference, here's the question we would ask. If the true population mean were equal to the threshold value, 35, right on the border between too weak and strong enough, how unusual would it be to see a sample mean like the one we saw, or one even more indicative of a strong enough fighting force? This would equal the area under the normal curve to the right of our observed sample mean. This area is the probability that if the true population mean combat score were right on the border between too weak and strong enough, we'd see a sample mean combat score like ours, or even more extreme than ours. If this probability were small, then our observed sample mean would be unusual, unlikely to have been seen. Not that it would be impossible to have been seen, but unlikely. If our observed sample mean is unlikely enough, far enough out in the tail of this assumed sampling distribution, then we can be confident in concluding that this sampling distribution doesn't belong where we've assumed it does. What we've just done is an example of statistical inference. Specifically, we've formulated Blorg's task in terms of two competing hypotheses. The null hypothesis is that the population mean combat score is right on the threshold between too weak and strong enough. The alternative hypothesis is the one Blorg will be happy with, that the population mean is greater than this threshold value. To test these hypotheses and make a formal decision, we slide the sampling distribution over to be centered at the null value, and then we ask how likely would it be for us to have seen data like ours by random chance. If this likelihood, technically a probability, is small, Blorg can be confident that his fighting force is strong enough. In statistical terms, we would say Blorg can confidently reject the null hypothesis. A hypothesis test like this depends heavily on our understanding of a sampling distribution. So remember, sampling distributions are the key to carrying out statistical inference.